A very interesting topic, a new topic, problems in computation. Okay. Now, when you think about problems in computation or problems in computer science, they mainly fall into two categories. You call them solvable and unsolvable. Now, when you think about solvable problems are those problems which you have a solution, and you have an algorithm to do it. Very simple, like, you add up two numbers or you find the factorial of two numbers. You have a methodology to do it. You have an algorithm to do it. Such a problem, you say it is a solvable problem, where you have a solution, you know that the solution exists. Not only you know that the solution exists, you have an algorithm, you have a methodology to solve that problem. You say it is a solvable problem. So let us see, what do you mean by unsolvable problem? Unsolvable problems, they are problems which are quite complex. You have no idea how to do it. You have no idea how to do it. Okay. Let's say division by zero, time traveling, even though you have movies, you have stories and all about time traveling. Actually, it comes under the category of unsolvable problems. Like, there is no actual algorithm to do a time traveling. Or, imagine I clap my hands. And, I say, when I clap my hands, all of you have to disappear. And the next clap of my hands, all of you have to come back again. Those are actually unsolvable problems, counting the stars in the sky. All those, they are called unsolvable problems. So these are the main categories in computation when you talk about problems. They can either be solvable or they cannot be unsolvable. Now, before we go into detail about solvable and unsolvable problems, there's a very pretty picture over there. It is the city of Konigsberg. The city of Konigsberg. It was in Prussia. Now it is in the current Russia. A very beautiful city with a lot of water bodies, and then small islands, markets, and all. A very pretty Russian city. Now, it was actually in this Russian city of Konigsberg that the graph theory took birth. Now, in the city of Konigsberg, there were 7 bridges. Okay, what you see in blue, they are the water bodies. And then the things which you see in green, they are the bridges over there in Konigsberg. Okay, so you have these bridges connecting, okay, this part of the land and this part. Again, you have, actually there were 7 bridges, 1, 2, 3, 4, 5, 6, 7. This is a picture of the 17th century. Now all these bridges are not there. There was the World War and all that. Many of the bridges have gone. Some bridges were renovated. I think only 2-3 bridges of the original 7 bridges are there. But anyway, this is where the original graph theory took birth. There was the city of Konigsberg, and then you had many bridges connecting the various lands between the water bodies. And in those times, those 17th century times, there was a game. There was a game like, you start anywhere. You start in any piece of land. Okay, let's say you start over here. Okay, you start over here, travel through all the bridges, exactly once, and then come back to the point where you started. Oh my God, I wasn't, I started over here, and then I ended up over here. I cannot, no, I couldn't. Let me start in a different way. I start over here, I come here, I go like this, I go like this, I go like this. Oh, I again need to cross a bridge. This bridge wasn't covered. Okay, so the question was, start in a particular point, travel through all the bridges exactly once, and then come back to where you started. Those days, there were lots of bets with money, without money, and all that. It was a very popular game. Like, people used to start running from one way to the other, and then, people couldn't try completing the problem, starting at a point, coming back at the same point. But, you have to cross all these bridges. So that is when this man called Leonhard Euler, he was a very great mathematician. He's in fact called the king of mathematics, king mathematician, one among the greatest mathematician of history. He not only was a mathematician, he was, he was almost well versed in all branches, like, think about geometry, calculus, algebra, trigonometry, number theory, be it physics, be it astronomy, whatever. Euler was a genius. Anyway, so this man called Euler, he thought, I need to find a solution for this. And the bridges, he tried to bring about a structure, like, for the bridges. And then, he came up with a simplified structure, the one you see over here in green, black, and blue. And then, the blue are the river bodies, and then the yellow are the bridges. So, he thought, I'll just name these. I'll name this A. I'll name this land body. The land bodies, he just simply named it A, B, C, D. And then he came up with a simplified structure. This A, he gave it, in a circle kind of a thing, A. And then he called this to be node or vertex. Okay. And then A had 5 bridges going out. One bridge, the second bridge, the third bridge, the fourth bridge, and the fifth bridge. And then this particular Konigsberg problem, we call it the Konigsberg problem, he was able to convert it into this kind of representation, where he did have something called vertices, and then the edges. Edges are nothing but the bridges which connect A to C, and so on. So this is how actually the graph theory came out. Euler, he propounded the graph theory. He is actually the creator of the graph theory. And this is the first graph in history. In mathematical history, this is the first graph. From the Konigsberg bridges, he was able to bring out this particular graph. And now he brought out a representation. And now his question was to solve the problem. Now he tried solving the problem. The problem is nothing but this. Start from a vertex A, go through each and every edge. Pass through the vertex only once and come back to my starting point. Okay. So there were 3 conditions. Start from any vertex, come back to the vertex, pass each edge exactly once. And that is what came up to something called the Euler cycle. Euler cycle is like, you pass through each and every edge exactly once and then come back to the starting point, Euler's cycle. Okay. Now, if you think logically, now let's come to the solution. Let's try giving a solution for this. Okay. Imagine you have a vertex, or you have a vertex called A. Okay. You go out from A. You should be able to come back to A. Okay. Then only that cycle will be completed. Okay. You should be able to go out from A and you should be able to come back to A. Now imagine you are able to go out and not come back to A. That cycle will not be completed. So very simple. How many ever times you go out, those many times you should be able to come back, which means the number of edges, the number of edges from a particular vertex, it should be even. Then only you can have a cycle. You can have a cycle only if the number of edges from each vertex is even. Imagine you can go out and then you can't come back, you will never have a cycle. Your cycle will be incomplete. But if you're able to go out and then travel somehow travel through any number of paths and all that, and then if you're able to come back to that particular vertex itself, you can say that you have a cycle. So similarly, each and every vertex over here, if they have even number of edges going out of it, you can have a cycle. Okay, now look here. Look here. Let's think about A. You have 1, 2, 3, 4, 5. There is no possibility of an Euler cycle in this particular graph. If any one vertex does not have even number of edges, your Euler cycle will not be satisfied. Okay, let's look each and everything. 1 itself dissatisfied, the cycle will not hold. Look here, C, dissatisfied. D, dissatisfied. B, dissatisfied. Very simple. You cannot have an Euler cycle, which means this problem, you do not have a solution. There is no solution for this problem. If I go back, okay, this Konigsberg problem, that game which they tried in the 17th century, it has no possible solution. You cannot start from a particular point. You cannot travel through each vertex. Sorry, you cannot travel through each edge exactly once, and you cannot come back to the same point. Euler proved it. Euler proved it mathematically. How did he prove it? He proved that, if you need to have a cycle, you should have even numbers coming out of it. You should have even number of edges coming out of it. And this particular Konigsberg bridge problem, it does not have even number of edges coming out of each vertex, which means, it is a problem which has no solution. But interestingly, Euler, he did not tell that this does not have a solution. Okay, he did not say that I cannot solve the problem. Instead, he said, I proved that this problem cannot be solved. I proved that this problem cannot be solved. Thus, this problem is solved. Chapter closed. Okay, this does not have a solution, correct? But Euler proved it. Euler proved it that it cannot be solved. Thus, this problem is solved. So there's no more discussions on this problem. Okay, this is a problem which cannot be solved, and I have proved it mathematically that it cannot be solved. Therefore, this problem is solved. So this is how Euler came up with a solution for a problem which did not have a solution. So let's come back to the problems in computer science. As I told you, problems in computer science are divided into two. Either they are solvable or unsolvable. Solvable problems, as we saw earlier, they will have an algorithm, they will have a procedure, and not only you get an answer for it, you need not always get an answer for a solvable problem. If you prove that there exists no solution for the problem, that problem, it comes under the category of a solvable problem. Example, a Konigsberg. Okay, there is no solution, but it has mathematically been proved that there is no solution, which means that problem is a solvable problem. So solvable problems are problems which have an algorithm, they will have a procedure, or it can be proved that there exists no possible solution for such a problem. Similarly, you even have a category called unsolvable problems. Now, these unsolvable problems, you can think of it like this. Imagine some 100 Euler's period. Euler's period, nobody would have ever thought of taking online classes, isn't it? Nobody would have thought of internet connection, students sitting at home, the teacher in her home. There is all this Wi-Fi and all that. I share my screen to you. 100 years back, that was something which people could have never thought about. But after a period of time, it is very much solvable. 100 years before, my online teaching, it was unsolvable. But 100 years down the line, 2020, the pandemic, online teaching is very much solvable. So unsolvable problems, they're actually a temporary status of a problem. For the time being, you cannot solve it. But might be, after some period of time, you might be able to solve it. You're not sure. You're not sure. You might solve it. You might not solve it. But as of now, with respect to time, when I clap my hands, you cannot disappear. With respect to time, I cannot count the stars in the sky, division by 0. I cannot do all that. Okay. So your category of unsolvable problems, they are actually the set of problems which for the time being, they cannot be solved. And whether it can be solved or cannot be solved, only time can tell. So those are the categories of unsolvable problems. Now, solvable problems, they are in two categories. You call them decidable and undecidable. Decidable problems and undecidable problems. Now, decidable problems are problems which have a procedure and an algorithm. Undecidable problems, they will have a procedure, but they will not have a problem. So before we go in detail into that, let me just give you a small idea about what is the difference between a procedure and an algorithm. Imagine you want to calculate 2 plus 2. You want to calculate 2 plus 2, sum of two numbers. Okay. Procedure is get a number, get another number, add it up, the result. That's the procedure. Okay. You have a methodology. Procedure is nothing but a methodology, a step-by-step process. If you have a step-by-step process to do it, it can either be decidable or undecidable. Algorithm means a procedure, it becomes an algorithm if I know the approximate time needed to do it. Okay, 2 plus 2, I know what time is needed. Okay, now if I know the procedure and if I even have an algorithm, if I'm able to calculate the approximate time, I say the problem is a decidable problem. Let's say you're sorting n numbers. You're doing a bubble sort. Imagine you're doing a bubble sort. You know how to do a bubble sort. Step by step, you know how to do it. Get n numbers, do the bubbling and all that. You know the procedure. You even have an algorithm. You are able to calculate. Let's say bubble sort, you have a complexity of O(n) square. Okay? You have an algorithm. Okay, you can find out how much time is needed. You can find out how much time is needed. It comes under the category of a decidable problem. Undecidable problem means you know how to do it. You know how to do it, but you do not know how much time it will take. You do not know how much time that particular thing will take. Let's say, imagine you're having a placement drive. You have all these colleges coming in. You have all these n number of colleges coming in, and Infosys, they are giving a common campus recruitment, a technical test for everybody, and all of you are appearing for the test. Okay, and imagine the question is, you want to become number one in that Infosys test. Okay, you want to become, all the colleges, they are giving a placement drive, or there are 1,000 number of students writing it. You want to become number one in that test. Okay, so what all should you be doing? Let's say you have to do preparation, you have to go on doing a lot of mocks, you have to learn your subjects. Okay, you know the procedure. Okay, you know the procedure how to clear Infosys. You know the procedure. You know the procedure. You very well know how to do it step by step. But are you exactly able to tell me within what period will you become number one? First attempt, you might not be number one. Second attempt, you might not be number one. You cannot tell the time. If you're lucky enough, you can be first time. Okay, if you're a bit more unlucky, you might be third time. But my question is, you should be number one in Kerala writing the Infosys exam. Okay, that is a bit difficult. You cannot tell the time. You might always qualify for the Infosys exam, but becoming number one, that is my question. You exactly cannot tell me a time in which you can become number one. So I say an algorithm for that does not exist. Okay, getting into Infosys, yeah, that will happen. But becoming the number one rank in Infosys, I say an algorithm does not exist for it. A procedure exists, algorithm doesn't exist. You do not have a time frame. You say it is an undecidable problem. Getting into Infosys, yeah, that is possible. But getting the number one rank in Infosys, because I don't have an algorithm for that, it becomes an undecidable problem. Imagine you want to become the Chief Minister of India. You want to become the Chief Minister of India, Chief Minister of Kerala. Okay, you know what to do. You should go into some you should be publicly a known figure. You should have a bit of politics, XYZ. You do a lot of social work. You get to know with a lot about people and all that. You are engaged in their matters. You very well know the procedure how to get it. But can you tell me a time frame? Can you tell me within 5 years will you be able to become the chief minister? Or might be within 20 years will you be able to become the chief minister? You cannot tell me a time. You cannot tell me a time limit for it. So it is an undecidable problem. Okay, almost all the mathematical problems, they become undecidable. Like just imagine you're thinking about a spanning tree, minimum spanning tree. Okay, find the minimum spanning tree. You're given a tree, find the minimum spanning tree. You know that ding dong bell, 3 steps finished, you will be able to find the minimum spanning tree. You exactly know within 3 steps you will be able to find out. You have a formula for that. You have a formula which will tell you the time. All such problems come under decidable problems. When you have a procedure and when you are able to tell the time frame in which you will be able to achieve it, approximate, not the exact, approximate time frame, you say it is a decidable problem. Undecidable problem, when you only have a procedure, you do not have an algorithm. Okay, and then you need to get an answer, like, will you be able to achieve Infosys in your first attempt? No, you can't say yes or no, like, undecidable. You're not very sure because you don't have a mathematics for that. Undecidable. You need a yes or no answer, but you're not able to give it. Can you become the chief minister of Kerala within the next 10 years? Yeah, you know how to do it, but you don't know the time frame in which you will achieve it. You can't give me a yes or no answer. Okay, all those kind of problems, they come under undecidable problems. They are even called to be non-computable. You cannot compute it, or they're called non-computational problems. So very simple, non-computational problems in computation are those solvable problems which are undecidable because you have a procedure, you do not have an algorithm, and it needs a yes or no answer, but you are unable to give it at the particular time, you call it to be a non-computational problem.